Hi y'all. Today I'm gonna just solve the quiz for a quiz for organic chemistry 2 on reductions, oxidations, Grignards. So the first thing is when a question is asking to propose the reagents, the first thing I try to do is identify the difference. And when I look at the difference from here to here, I see that basically on this carbon, we've added bonds to oxygen, 2 bonds to oxygen, and that's the only difference. So we've added 2 bonds to oxygen, so that must be an oxidation. And if we have an oxidation reaction, I know that I can use KMNO4 in hot conditions usually, PCC or Jones reagent. Those are different types of oxidizing agents, but KMNO4 doesn't work well if you also have a double bond because it'll just oxidize everything. We don't have a double bond in this case, so it should be fine. PCC, for primary alcohols, it stops at the aldehyde. It's a weaker oxidizing agent. So I'm just going to check and make sure that we don't have a primary alcohol. And when I look at this is a primary alcohol. We look at where the alcohol is attached and how many carbons is that attached to. And so that is that is just one. So it's primary alcohol. So we can't use PCC because it doesn't stop out. It just adds 1 bond to oxygen, not 2. It takes that beta hydrogen and turns 1 into oxygen, but not 2. So PCC wouldn't work. Or the other one would be Jones reagent. That should be fine. So either KMNO4 or Jones reagent. And with KMNO4, this is typically done with KMNO4. This is typically done in heat, and then usually you'll also have a hydroxide, and then you need some kind of acid as a step 2. But I think if you got KMNO4 and then with the acid of some kind, you got full credit, or if you did Jones reagent. But if not, then if you forgot to put the acid, then I think I counted off like 1/4 of a point, maybe something like that. And then what is the name of this type of reduction? This is called reaction. This is called an oxidation reaction, which I already mentioned over there. We're increasing the number of bonds of oxygen. This was not a question on the quiz, but just as a reminder, if you start with a primary alcohol and you trade out one of these beta hydrogens and this hydrogen over here for an oxygen bond, we get an aldehyde, but aldehydes are very quickly oxidized to carboxylic acids unless you have PCC. So that's the oxidation. If you're doing it the other way, reduction, it kind of goes backwards, where you start with a carboxylic acid, go to aldehyde, and go to a primary alcohol. Or if you have a secondary alcohol, it will go to a ketone, and that's as far as it can go. So for ketones, you can use any reagent. Okay. And then for the next one, this is a multi-step reaction. So the first one, when I see an aromatic ring, I automatically think electrophilic aromatic substitution. And in electrophilic aromatic substitution, if we have a halogen and some kind of Lewis acid, it's going to add a bromine. Doesn't matter where the bromine adds because it'll be the same all the way around the ring. And bromines, if we're doing a reaction with a bromine, that is going to be an orthopara director, even though it is slightly withdrawing. So it's like deactivating, but it still is an orthopara director. It's one of the exceptions. So then your AlCl3 with your acyl, I just totally lost my train of thought. Then if we react this with AlCl3, which is a Lewis acid, and an acyl chloride, so basically this carbonyl group, that's a Friedel-Crafts acylation. And that will, because we're doing a reaction on this, it'll either go ortho or para. So either one of those would be right. I would give credit for ortho or para. And if you did this, or if you did ortho, either one of those would be correct. So if you did either one of those, you should get points for that. And then whichever one you did from there, so you have a ketone, and then if we reduce a ketone, that will become a secondary alcohol. So either ortho or para, whatever you had in the first place, and then this becomes alcohol. The first step is you don't have to draw the mechanism, but the hydride would attack right here as a nucleophile, kick that bond up and give you O-, and then you add the acid. So this or this you would get credit for. Either of those is fine. Okay. And then question on the back. For the following reaction, draw the Grignard reagent that is formed after step 1. So the Grignard reagent formed after step 1, the magnesium would just insert itself right here between the bromine and the carbon. And then using proper curved arrows, draw the reaction mechanism of the reaction between the Grignard and the given ester. So you have to have all the proper curved arrows for this. So this would be 1 point. And then the curved arrows would also be worth credit. O-, and we have our, sorry, that's a single bond. Our new bond made from here to that carbonyl carbon. Always when we have any nucleophile, which we know Grignard reagents are basically the equivalent of a carbanion, that will attack at the carbonyl carbon, and then this bond will break. So you get something like this. I didn't mean to draw that a wedge. I just drew a bad line. So we get this structure right here. But if this can act as a good leaving group, if an ester can act as a good leaving group, it will leave. And they're not good leaving groups on like SN1, SN2 reactions, but they will leave after a carboxylic acid reaction. And then we get this, but if we have excess of our Grignard reagent, which we assume we do, then we get another reaction to get another O- and another one of these. Now, if you add acid, that will become an alcohol. I won't count off points if you made it into an alcohol. Technically, it doesn't have the acid included. So I would take either of these as the right answer. Okay, and then why can't Grignard reagents be used in the presence of water? Because it's very reactive. So essentially, the Grignard reagent, if we think of an acid-base reaction plus alcohol or water, in this case, the Grignard is the base, and so it would take this hydrogen and leave the alkane fully saturated with the hydrogen and OH-. And so that would be what would happen if you had Grignard in the presence of water, but that could be a reversible reaction. You have to go based on pK to see which side is favored, because technically this reaction is in equilibrium. So the pK of this is 15.7, while the pK over here is 50. So the weaker acid is favored. So that would mean that your left is favored. So wait, what did I just do? The side with the weaker acid is favored. So this is 15.7. The weaker acid is 50. I don't know what I was thinking. Sorry. This side would be favored. So because of that, anytime you put Grignard in water, it automatically will just break down into this and make it, or react to form this and make it much less strong. So because of that, you can put that as the right answer if you want, or you can say it reacts with water or it is neutralized by water. Any of those would be fine. And that is that's the video key for this quiz. I hope that was helpful. See you in class.